Achha, so listen, we had started with mass spectroscopy, and I told you, okay, you have a molecule, and that molecule, you add that molecule into this chamber over here, ionize karte usse, it turns into an ion that's known as a molecular ion. Or it might break down into tiny fragments. This big molecule over here might break down into very, very small, tiny fragments. And remember, each fragment would be a part of the bigger molecule. So it wouldn't be some, मतलब कोई नए किस्म का fragment नहीं होगा. It would be just some piece of the original molecule. So you will have all these tiny fragments. And those ions are passed through or deflected through a magnetic field. And deflection is inversely proportional to mass. So which means that heavier particles would be deflected less and light particles would be deflected more. So the molecular ion, that is the heaviest one. So that is going to be deflected the least. And subsequently, very light particles would be deflected by a very large margin. So this is what will happen. And based on the deflection, you can figure out the mass of the particles. That is how you measure the mass of molecules, AR, MR, etc. That is how you measure it. Like, how do you know that magnesium is twice as heavy as carbon? Because deflection uski kam hogi. It's going to be deflected less compared to carbon. So what you do is, this is how you measure the mass of particles, whether it's the AR or MR. So this is probably the only thing that we had done so far. And the next thing is, how would the mass spectroscopy show these results? The mass spectroscopy will have two axes. One of them would be abundance. So it's going to have a y-axis and a z-axis. Just a second. So your y-axis and x-axis. So this one. Here's your y-axis. Here's your x-axis. And this axis is known as the mass. This axis has mass on it. This is written as m over e, where e is the charge. You can simply state that this is mass. Why? Because all the charges are +1, so it's the mass to charge ratio. So, and the other axis, the y-axis, is your abundance. It's your percentage abundance or relative abundance. Now, there would be detectors over here. They'll be detecting these charged particles in the form of current. They're going to, if you have charged particles moving, that's basically a current. That is a current or electricity is flowing. Like if there's charged particle, that's basically moving charges is current. So the detector over here will detect a current. The size of the current is going to determine how many particles are coming. So if there's a lot of these particles, you're going to get a big peak. Ethanoic acid, I think, is 60. CH3 is 12 plus 3, 15. 15 plus COH, that's 45. So the biggest or the heaviest peak would be for the molecular ion, which is the M peak. You're going to get that at 60. That's your M peak. And a certain amount of detection would happen. A certain percentage of particles would be detected, depending on, and it depends. Maybe there's going to be a lot of molecular ion, maybe there's going to be very few molecular ion. So you might detect something at 45. So there would be fragments that would be detected at 45. OH, I think, is 17. So you might detect something at 17 as well. Having a mass of 17, you might detect something at OH is 17, CH3 is 15. And I did CH2 as well, so that's 14. So you'll have all these particles, and the amount of particles that you will be detecting would be just random, because the fragmentation will happen in a random order. Like, you can't really predict how the original molecule will break down. I mean, you can't really, I mean, every time it's going to break down in a different way. The beam of particles would, I mean, you will ionize this and the molecule will break down. So every time it's going to be different. So you can't always predict how or which particles are formed and in what quantity are they going to be formed. So these peaks would be random. They would be, I mean, and they would have no specific meaning. The percentage of abundance, it will just tell you that, like, you got 10 particles of this, you got 2 particles of this, you got 20 particles of this, and so on. So this is how the graph would look like. This axis over here is the mass or mass to charge ratio. The charge is +1, so that doesn't really matter. It's basically the mass. So is this clear? This graph over here, is this clear? Pakio clear है? Mahad, is this clear? Alicia, Amna, is this clear?
नहीं, नीचे परसेंटेजेस हैं, ऊपर परसेंटेजेस है y एक्सिस पे और x एक्सिस पे जो है वो हमारा
mass
कि मतलब mass है. ठीक है.
और mass हमने किस तरह निकाला? Mass we found out के the deflection can be converted into mass. Less deflection, so more mass. So ऊपर percentages हैं कि how many particles, like if you had 100 particles coming from that side, तो उनमें से 10 particles were this one, so that's 10%. This might be 50 particles, might be this one, 20 might be this one, 10 would be this one, and so on. Okay. So and remember the height is going to be random. It's fragment percentages are random. Okay. So
सर ये जो m peaks है ये तो डिफरेंट है ना, ये 45 तक हमें परसेंटेजेस 100% तक है, उससे आगे तो डिफरेंट है.
क्या मतलब?
तो मतलब जो ये आपने रेड में बनाया हुआ ये हमारा 100% तक है ना, इसमें हमें पता चलेगा कि मतलब कौन कितना परसेंट है.
नहीं, उसमें ये भी शामिल है ना, सारे शामिल
जिससे
है.
ये भी जो m peak है वो तो कुछ और ही है ना.
नहीं, वो अलग नहीं है, वो भी इसका पार्ट है ना, मतलब उस बीम के पार्ट ही है ना. मतलब अगर मैंने 100 particles, if I detected 100 particles, so some of them would be this one, some would be this one, so all these particles, मतलब कोई random order होगा. ठीक है. So fragmentation, remember, is random. So fragmentation is random, and the percentages can vary. Okay. So the percentage of fragments or percentage abundance, like how many fragments are formed, it also varies. Now fragmentation, let's focus on fragmentation first. Fragmentation gives you a very good idea of now we're going to do the reverse. So I have this graph. The fragmentation gives you a very good idea of what this molecule could be. I mean, for example, let's imagine we didn't know it was ethanoic acid. Let's imagine we had no idea that it was ethanoic acid. And what we are given is just this graph. And so I'm going to do the reverse now. Because fragments give you it's like solving a puzzle. Fragments give you a very good idea of what the molecule might look like. Because remember, these are small pieces of the same molecule. You got a 14, you got a 15, you got a 17, you got a 45, and you got a 60. So what you can do is you can think of it as a jigsaw puzzle. Like, I mean, this is the big molecule over here, and all these small molecules are just pieces of this big molecule. So if you can kind of solve the puzzle and put them together in the right way, you can figure out what this 60 is. So we can, and let's say the information is given that it has carbon, hydrogen, and oxygen. So let's say this information is already provided that it's got carbon, hydrogen, and oxygen. I mean, this information is also usually obtained from the mass spectroscopy. Although in this case, I just made 5 fragments because remember the fragmentation could be, I mean, you could have a number of fragments. Like it's not just this, you could have any number of fragments. You could have had a CH fragment. But remember, not all fragments are usually formed. Fragmentation is completely random. Sometimes some fragments are formed, sometimes the other fragments are formed. So So the number of ways the molecule could fragment could be many different ways. And even the identity of the atoms can be obtained over here. You might get a single hydrogen atom as well. So you might get some detection at 1, you might get a detection at 16, you might get a detection at 12 as well. So based on this, let's assume that we have or we know that it's got carbon, hydrogen, oxygen. So what I'm going to do is I'm going to try and figure out what this 14 is, the smallest one. Now, based on the atoms I've got, the only possibility I have is, the only possibility I've got is it might be a combination of carbon and hydrogen. So it must be CH2, right? Because there's no other combination that would work. So that means the molecule has a CH2 fragment. What about 15? What could be 15? 15 could be, it could be, I mean, that's the only possibility. It has to be CH3 plus 1 that only has a mass of 15. What about 17? Now for 17, what combinations can I have? Like I've got carbon, hydrogen, oxygen, so I can have OH, that could be 17, right? And there's no other combination that would work. Like CH4 is 16, we don't have CH5. There's no such thing as CH5. I mean, CH5 is structurally incorrect. Like, I mean, you can't have CH5. So that doesn't make sense. Then what about 45 then? So you can think of different arrangements where you can get 45. And some of them, like you could have COH. I mean, that's obviously 45. We know that it's CO, but you could have some other combination as well. Like CO is what? CO is 12 plus 16, that's 28. Maybe there's a CH3 on one side. So that is 15 plus 28. So this is, what is 15 plus 28? That's 43. And maybe there is, so maybe, I mean, maybe this is 45. I'm not sure if this is 45. It's 29 plus, that's not actually, is this 45? That's way more than 45. What is this? 12 plus 16, that's 28. 28 plus 12, that's 43. I can't have 45 for this because if I add another C to this, like if I draw this, because remember 45 is like solving a puzzle. So if I draw this CH3 with CH3 and I said CO, this is 43. I can add an H, that would make it 44, but remember that's not a fragment, that's a whole molecule. So I can't really have that. If I add another C over here instead, that would make it a lot more than. So I think any combination, I mean, the only combination of atoms that you've got is this one. That's the only one that's going to give you 45. And then by looking at all the fragments, you're going to figure out or guess. So you're going to guess or figure out what is 60. So you know there's a COH, you know there's a CH3. So probably if you try and recombine them, it's probably going to be this one. So that is 60. So are you getting my point that you will be shown just this? And there would be some random molecule whose mass spectroscopy is done. The molecule would have small pieces that would be detected, and it would, I mean, the entire molecule would be intact as well. You'll know the mass of the small pieces. You can figure out the masses of or the structure of the small pieces, and then you can kind of combine them to form the bigger piece. So is this point clear?
Yes, sir.
Okay, so let's do this fragmentation thing. So there's a question which we can try. And in the question, you've got, they've told you that there's a molecule. And I'm actually, I said, in that question, I would have to do some math first. So in that question, they're telling us that there's a molecule which has the formula. It's Si X, Cl is Y, and O is Z. Now, O is Z. So you have no idea how many silicons, how many chlorines, how many oxygens you've got. What you have to do is you have to figure out what this molecule is. And remember this, the structure has to make sense. When you draw the structure, remember this silicon makes 4 bonds. So it makes 4 bonds. Cl over here makes just 1 bond. And oxygen over here makes 2 bonds. So you've got silicon, chlorine, and oxygen. And what's given is they've told us that it's got silicon, chlorine, and oxygen. And they've given us they've done a mass spectroscopy of that molecule. And you're getting all sorts of detections at different masses. So this is the percentage of the particles that are getting detected. And the first particle that they got was, they got a detection at 133. Then they got a detection of another particle at 149. And let me do some math as well, just a second. Then I think it was 247. They detected a particle at 247. Then they detected a particle at 263 as well. And after that, it was 396. I hope it's right. 396, 263. That's 396. And you got all sorts of detections. You got you got all sorts of detections. Now, sorry. So now the next part, which is you got to figure out what this molecule is, and you have to figure out the exact structure. So can anyone try and tell me what this 133 is? Like, let's detect the smallest particle. Like, let's try and figure out what the structure, I mean, what could this be? We know it's a molecule that contains silicon, chlorine, and oxygen, and I'll tell you the masses as well. Silicon has a mass of 28. Chlorine has a mass of 35. And oxygen over here has a mass of 16. So can anyone try and work this out? I'll give you just 2-3 minutes. Try and work this out. What could be 133 like? I mean, the fragment doesn't need to have all the atoms. It's just going to be a tiny piece. It might have silicon and chlorine, might have chlorine and oxygen. So we need to come up with 133. What's 133 in a sensible way? So you can try this for 2 minutes. Find out what's 133. And you would need a calculator for this. I said, did you try and do this? ठीक है. Anyone else?
S2Cl3.
कितना?
सर मेरा जितना बना है मैंने 3 times 35 को प्लस किया और प्लस 28 किया तो वो 3 बन रहा था.
अच्छा, इसका मतलब है it's 1 silicon and 3 Cls, right? तो so that is 133, right? अच्छा, remember fragments होते हैं वो incomplete होते हैं, ठीक है, because they're small broken pieces, so the bonds are always incomplete. So it's SiCl3, right? And structurally that is correct. Silicon needs one more bond. Now figuring out 149 would be easy. Like, what's the difference between 133 and 149? कितने का difference है? Like it's a difference of 16, right?
Yes sir, 16.
तो इसका मतलब है this one over here is it's just going to be a slightly bigger fragment. It's going to be the same molecule, which is 133. और उसमें आपने क्या add करना है? You just have to add 16 to it, which is what? Which is oxygen, ठीक है? So all you have to do is you have to add one extra oxygen over here. So that's it. Achha, then you have 247. So 247 is an even bigger fragment. So can you figure out what 247 is? Like, इसी में कोई और चीज add कर लो, तो you get 247. Like, what do you need to add?
तो 98 ऐड करना है.
ठीक है, so you need to add 98. You'll get a bigger fragment. So it's just going to be a bigger piece, ठीक है, of the original molecule. So what do 98? How do I add 98 to this? Think, what is 98?
Say 2 times chlorine and 1 times Si.
ठीक है, so 1 Si and 2 Cls, तो वो फिर 98 हो जाता है. So you got so that is 98, right? So 247 is this one. So we're almost about to complete our puzzle. So what is 263 now? That's one more.
ऑक्सीजन से 16.
ठीक है, तो बस 16 है, तो इसके अंदर इसी के ऊपर आगे कर लेते हैं कि एक सेकेंड इसको कर लेते हैं साइड पे. अच्छा, तो इसमें ऑक्सीजन लगाना है, ठीक है. There's going to be one more oxygen, and finally you have last में क्या है? 396. अब कितना डिफरेंस है? You need to add.
सर इसमें 263 में हम लोग वापस 133 वाला लगा देंगे तो हमारा पूरा 396 बन जाएगा.
ठीक है, तो एंड में SiCl3 दोबारा लगा दो. It's going to be Si and 3 Cls, right? So this is your bigger, वो जो MP के ना molecular ion. This is the molecular ion. The rest were all fragments, tiny fragments that broke down when the fragmentation happened. Is this clear?
Yes sir.
So remember, you can guess a lot about fragments. अच्छा, ये हम organic में ना isomers पढ़ते रहते हैं. उसका भी purpose यही होता है. मतलब isomers क्यों पढ़ते हैं कि same molecular formula, different structure? क्योंकि remember कि when you look at a molecule, like look at any molecule, like I mean look at your fingernails. You don't know what the structure is. I mean you can't see it. You can't see the atoms, right? So it's all guesswork. It's like solving a puzzle. तो इसलिए आप isomers, organic में isomers आप इसलिए पढ़ते हो कि when you study isomers, you figure out how to sort of arrange atoms, right? That's why isomers are important, and isomers are going to be very important in this as well. Okay, I mean there would have been a number of ways in this these atoms could have been arranged, right? So this is where isomers comes into action. Like whenever you study organic chemistry, how do you figure out like this, like what's the structure, what is the molecule that your nails are made up of? I mean, this is what you do. You do mass spectroscopy, and then you try and figure out what are these small pieces, what is this big piece? TK, you start to kind of arrange all the atoms in different ways and try to form this bigger molecule. There are other techniques that will help us as well, but this is one of them. TK, remember you've got several different techniques, so this is just one of them. So let's try another molecule, and this time I'm going to pick. Let's do a simpler one. So I've got a mass spectroscopy, and I have to figure out what the molecule is. I've got as a mass to charge ratio, and on this side it's the percentage abundance. So you're getting a detection at 14. You're getting a detection at 16. So then you're getting a detection at 28. You're getting a detection at 30 as well. And then there's the molecular peak, which is 44, I think. 44, 44. So you're getting a molecular peak at 44. Just let me think about it. TK, 44 is fine. And there's a random bunch of particles that you have detected. Some of this, some of this. TK, that's the percentage of particles that you've detected. Anyways, what is this 44 now? Try and work this out. And first thing, what is 14? And remember, these are all the fragments. These are all the possible fragments that have formed. So there's nothing missing here. So what is 14? Like which particle has a mass of 14?
periodic table से ही देखना है.
हाँ, तो 14 क्या होता है वैसे? याद होना चाहिए. 14 is?
So 16 to oxygen है, 14
नहीं, nitrogen.
Nitrogen.
So it's a fragment of nitrogen. ठीक है. अच्छा, remember one thing. Make sure that whenever you talk about fragments, put a positive charge, because you're detecting. I mean, make sure you add a positive charge. Because this is positively charged. You're detecting positively charged fragments. TK, make sure you, whenever you write this in paper as well, make sure you put a positive charge on that. So anyway, 16 is oxygen. So what is 28?
The N2.
Okay, so remember, the small fragments would join up to form these bigger fragments. So that must be N2. What is 30?
So nitrogen plus oxygen.
Okay, that's NO. And what's the big one now? 44. Remember, the small pieces would add up to form this big piece. So that is. Okay, so that's fine. So this one is N2O. Okay, that's your big piece. It's going to be N2O. All these pieces were basically part of, I mean, you can break an NO piece from it, you can break an N2 piece from it, you can break an N atom, an oxygen atom. The reason we didn't have hydrogen or any other atom over here was because agar hydrogen hota, you must have detected something at a mass of 1. Carbon hota, so must have been some detection at 12 as well. So the smallest piece is usually atoms. Most of the time, that's the atom. So is this question clear, this one?
सर इन पे प्लस चार्ज इसलिए आ रहा है क्योंकि हमने इनकी
हाँ mass spectroscopy कर रहे हैं ना, तो यहाँ पे क्या था कि जो fragments always had a positive charge. उसकी कोई significance नहीं है, वो बस just write the positive charge because that is how they are detected. Is that clear?
Yes, sir.
Now the next one, moving on, things are going to become slightly more complicated now. Because remember, doing this is kind of difficult. Like it's especially, I mean, it works for small molecules. It works perfectly for small molecules. For big molecules, it becomes kind of difficult. For very big molecules, it becomes even more difficult. So the thing is, your technique, this one, it's not going to work always. For small molecules, it's going to work perfectly. Like for big molecules, there would be so many combinations that it becomes harder and harder to actually detect. I mean, वो puzzles की तरह ना कि अगर एक puzzle में 5 पीस है तो वो आप बड़े आराम से solve कर लेते हो, लेकिन एक puzzle में अगर 1500 pieces तो obviously उसको बहुत time लगेगा और बहुत मुश्किल होगा solve करना. तो वही चीज इस पे भी apply होती है. So this is not effective always. Acha, but there would be things that would help us in this, and that has a lot to do with probability. So we'll start discussing a bit of probability now as well. The very first thing is using mass spectroscopy. We can figure out the first thing. Let's talk about the first thing. Carbon pehle kar lete hain. Achha, so we can figure out the number of carbon atoms. Achha, why specifically? Why would that be helpful? That's going to be helpful. Why? Because almost everything on planet Earth, especially living organisms, plants, animals, humans, we're all carbon compounds. So chemistry of life revolves around carbon compounds. That is something that would be very useful because we're usually not studying inorganic compounds. We're mostly interested in organic compounds. We're doing this in medicine, viruses, everything is made up of carbon. Now, when it comes to carbon atoms, so when it comes to carbon atoms, carbon has an isotope as well. Carbon has a mass of 12, and carbon also has a mass of 13 as well. It's got 2 isotopes. Actually, it's got a lot more than 2. If I यहाँ पे ना carbon, and I'll just Google carbon isotopes. So, I mean, you can see it's got, I mean, atoms have all sorts of isotopes. So you can, if you see over here, carbon has 15 known isotopes. So there are 15 isotopes. It starts from C8 to C22, but the ones that are stable are C12 and C13. So, and the percentages are also given. Like C12 has a percentage abundance of 98.93%. That's quoted over here. That means if you have 100 carbon atoms, then almost 99 of them are carbon 12. And carbon 13, its abundance is also given. So out of every 100 atom, almost 1%, like if you have 100 carbon atoms, one of them is going to be carbon 13. So if we are made up of carbon, then that means 1% of the atoms in our body that are carbon atoms are actually carbon 13. So carbon has these 2 isotopes. These are the more common ones. The other ones like C14 is very rare. It's I mean, if I just sort of click, so we don't talk about them because their abundance is almost negligible. Like I mean, carbon 13. I mean, carbon 14 is hardly present on Earth. Like it's occurs in trace amounts. Trace amounts means that it's almost non-existent. So coming back to this, carbon has two isotopes, 12 and 13. And I'm going to write down the probability as well. And I'm going to write, so this is 98.9%. And this one over here is 1.1%. ठीक है, यहाँ तक clear है? Is this clear? ठीक है? अच्छा, अब ये कि इसका करना क्या है? इसका पहले मैं थोड़ा सा brief idea देता हूँ. Remember, the mass is different. So if I have a CH4 molecule, and now I'm only focusing on the M peak. I don't care about the fragments. ठीक है? अच्छा, अब पूरा focus ना M peak के ऊपर है. तो मुझे बताओ कि molecular ion peak कितनी बनेंगी इसकी? I mean, if I do mass spectroscopy of this, it's going to form CH4 plus 1. Okay? So I'm just ignoring the fragments. There would be a lot of fragments formed as well. I mean, it would form a CH2 fragment, a CH fragment, a CH3 fragment, a hydrogen atom might break off. So lots of small fragments would be formed as well, but I don't care about them at the moment. So CH4 molecular ion peak, I'm just focusing on the M peak. अब मुझे बताओ कि इसकी mass क्या है? क्या mass आएगी mass spectroscopy में? Anyone के क्या mass आएगी इसकी CH4 की? और एक mass आएगी या दो masses आएंगी? I mean CH4, right? 16 होगा ना, मतलब लेकिन 16 तब होगा अगर कार्बन आप 12 ले रहे हो. कार्बन is 12 and hydrogen is 1 plus 1 plus 1, right? So 16 बन रहा है. What if carbon is 13? फिर क्या mass होगी? 17, right?
Yes, sir.
तो इसकी अब जो MP की जो mass होगी ना, वो दो टाइप्स की MPs होंगी. एक heavy होगा और एक थोड़ा light होगा. M peak की जो mass होगी, that's going to be 16. And there's going to be another peak which is known as the M plus 1 peak. मतलब M plus 1 इसलिए कहते हैं उसकी mass एक ज्यादा है. So remember, carbon, ये जो CH4 है ना, there are actually two different M peaks now. One of them is heavy and the other one is light. Is that clear? तो आपको ना आपको दो different particles detect हो रहे होंगे. Like one of them would be detected at 16 and the other one would be detected at 17. So both of them would be M peaks and there would be lots of fragments as well. So lots of small fragments, but we don't care about the fragments. So there's going to be an M peak and there's going to be an M plus 1 peak. दोनों ही M peak है, बस वो M plus 1 इसलिए है कि उसकी एक mass, एक उसकी mass ज़्यादा है, वो थोड़ा सा heavy है. अच्छा, percentage abundance क्या होगी? What is the probability of getting 16? Like, what is the chance of getting 16? कितनी probability है?
98%.
यानी almost 99%, ठीक है. And what's the probability of getting 17? मतलब carbon 13 आने के 1%, ठीक है. So that means कि 16 के ऊपर detection बहुत ज़्यादा होगी, ठीक है. और 17 के ऊपर detection जो होगी वो बहुत ही थोड़ी सी होगी. यानी almost it's 99 ratio. मतलब अगर मैं round figures use करूँ, it's going to be 99:1. Like 99% of the time you'll be getting 16. और वो 1% जो chance होगा ना, वो छोटी सी एक peak होगी इसकी, right? So that is 99:1. So your graph would kind of look like this. It's going to have M peak पहले हमने बनाई हुई थी, वो एक ही बनाई हुई थी, जिसे हमने खैर इस केस में तो एक ही है, कार्बन वाली है. हाँ, ये एथेरोइक एसिड था ना, तो हमने तो कहा था कि it was 60, right? One peak. It's not going to be one peak for etheroic acid. अब मुझे तो etheroic acid पे आ जाओ. I mean, this entire thing is 60, but it is only 60 if both carbons are 12. What if one of them is 13? तो क्या होगी peak? की mass क्या होगी? 61. And what if both of them are 13? Then it's going to come out to be 62. So actually, उसकी जो peaks होंगी ना, it's not going to be one unique peak. It's going to be at 60. There's going to be एक छोटी सी peak 61 पे भी होगी, and there's going to be an even tinier peak at 62 as well. Is that clear? This thing?
Yes, sir.
62 पे छोटी की होगी सबसे।
हाँ, वो अब मैं प्रोबेबिलिटी वो अगली क्लास में पढ़ेंगे, लेकिन मैं वैसे एक्सप्लेन कर देता हूँ। प्रोबेबिलिटी क्या है? आ जाओ इसके ऊपर आ जाओ कि दोनों 12 आने के चांसेस क्या है? कार्बन 12 एंड कार्बन 12। अगर प्रोबेबिलिटी मैथ में पढ़ी है, जब एंड आता है कि लेट्स से वो नहीं होता डाइज वाला के एक दफा 6 है और दूसरी दफा भी 6 है, जब एंड आए ना तो क्या होता है? मल्टीप्लिकेशन होती है प्रोबेबिलिटीज की, तो 99% इंटू 99% हो जाएगा। ठीक है, सो दोनों कार्बन 12। अगर दोनों कार्बन 13 लाने हैं तो उसकी प्रोबेबिलिटी क्या होगी? इट्स गोइंग टू बी कार्बन 13 आने के चांसेस क्या है? दैट्स 1%। दूसरा कार्बन 13 आने के चांसेस क्या है? वो भी 1% है। तो 1% एंड द सेकंड वन इज आल्सो कार्बन 13, सो दैट इज आल्सो 1%। तो 1/100 इंटू 1/100, तो प्रोबेबिलिटी क्या होगी? बहुत छोटी होगी। मतलब 1/100 इंटू 1/100 करो तो 1/10,000 बन जाता है। क्लियर है?
Yes, sir.
अच्छा खैर, ये प्रोबेबिलिटीज
ये
हम अगली क्लास में पढ़ेंगे। अभी तो बस याद रख लो कि बाकी पीक्स छोटी होंगी, क्योंकि कार्बन 13 आने के चांसेस ज्यादा है, तो बहुत कम है। मतलब मेनली तो चांस कार्बन 12 आने का ही है ना, कि वो 12 और 12 होंगे तो इट्स गोइंग टू बी 60। एक उसमें से 13 आ जाए तो उसकी प्रोबेबिलिटी मतलब बहुत ही कम है। और अगर दोनों 13 है उसकी प्रोबेबिलिटी और भी कम है, क्योंकि वो कार्बन 13 तो वैसे ही बहुत रेयर है। तो प्रोबेबिलिटीज के ऊपर ना कल बात करेंगे, ठीक है? और ये बस ये होगा कि जो आपकी मॉलिक्यूलर पीक होगी ना, दैट्स नॉट गोइंग टू बी वन सिंगल पीक। सो वील जस्ट फोकस ऑन द मॉलिक्यूलर पीक। हाउ कैन यू फिगर आउट द नंबर ऑफ कार्बन एटम्स बाय जस्ट लुकिंग एट द एम पीक्स? एमपी की जो डिस्ट्रीब्यूशन होगी ना, उससे यू कैन फिगर आउट कि हाउ मेनी कार्बन्स यू गॉट। ये फिर कल हम डिस्कस करते हैं, ठीक है? चलिए ठीक है, लेट्स कंटिन्यू टुमारो देन। टेक केयर, अल्लाह हाफिज।
अल्लाह हाफिज़।